Okay, so good evening, everyone, and welcome to today's very special uh, colloquium. This is called IPA-IOP Cockroft Walton Special Asset Colloquium. It's a long title, but it also says the collaboration of several agencies in bringing out this very special colloquium. And right away, I would like to invite Professor Vandana Nanal, who is the General Secretary of Indian Physics Association, to say a few words about this particular series, and also go on to invite and introduce Dr. Andy Turner, who is today's speaker from University of Reading, UK. So over to Vandana.
Thank you, Satya, and thank you for helping us organize this ASET colloquium. It's my pleasure to invite you all for this IPA-IOP Cockroft Walton lecture series. As many of you know, this exchange program between Indian Physics Association India and Indian Institute of Physics UK was set up in 1998 by generous support from DAE and Tata Trust. The program runs with an idea that on alternate years, the eminent scientists from UK and India visit each other and give a series of lectures. In India, these lectures are called Cockroft-Walton lectures, whereas in UK, they are called Bhabha lectures. Most of you would know about Cockroft and Walton, but for the youngsters, just to introduce them, so Sir John Cockroft and Ernest Walton got Nobel Prize in 1951 for the discovery of the Cockroft-Walton voltage multiplier, which this was essentially one of the first accelerators which they built in 1932. And using this high voltage multiplier accelerator, using a 300 MeV proton, 300 keV proton, 400 keV proton beam, they actually bombarded it on lithium target, and the target was broken into 2 alpha particles. This was the first man-made reaction. And later this cascade generator was very machine also known as cascade generator was very useful. Even today it is used as a neutron generator in many parts. So on the right here you see a picture of Dr. Homi Bhabha with the cascade generator, which was installed at TIFR, and it was here till early 80s. And as many old timers in TIFR know, that the part of the hall where it was installed, which later became a Pelletron user hall, is still called Cascade Hall. So with this intro, this year in 2020, we have very fortunate to have Dr. Andy Turner as a speaker for Cockroft Walton Lecture Series 2020. And he was due to visit us in March, April, but until the COVID put the brakes on that. So we have, he has kindly agreed to have these lectures online, and there will be 3 lectures. So first is hosted by TIFR ASET Colloquium as a joint lecture. Second is hosted day after tomorrow by University of Hyderabad, and a third one on 30th October, which is also happens to be Dr. Bhabha's birthday, by IIT Ropar. So let me briefly introduce today's speaker. So Andy is an associate professor in monsoon systems, funded jointly by the University of Reading's Academic Investment Program and National Center for Atmospheric Sciences, based in the Department of Meteorology. Prior to this, he got his PhD in meteorology from University of Reading. His general interests are in monsoon variability, predictability, and prediction, including the interaction between monsoon systems and other elements of the climate system. He was co-chair of the GVEX Clever Monsoon Panel, is an associate editor of the Quarterly Journal of the Royal Meteorological Society, and a lead author of the forthcoming Working Group 1 contribution of the 6th assessment report of the IPCC, that is Intergovernmental Panel for Climate Change. So, Andy, over to you.
Okay.
An exciting monsoon lecture.
Thank you very much for your very kind introduction. I'm just going to share my screen now. Excellent. Okay, looks like we've started. And thank you very much for the invitation, both for this series of seminars, but also for this particular lecture in particular in Mumbai. So I'm going to talk today about observing the Indian monsoon can we use those observations to solve the problem of monsoon prediction, which has been something that it has been very difficult over a number of years in many different countries, not least India. And through this seminar, I will talk also about our field campaign called Encompass that took place during 2016, where we came to India and did a lot of measurements. And please feel free to ask me any questions, or you can send me an email at the address on the screen here. All of the images shown on this front page are aspects of things that we saw during our field campaign in 2016, and we'll go back to see some of those later. But perhaps I can just draw your attention to the conditions that you yourselves will be very familiar with, the monsoon rains, which really have a great impact on all aspects of your life. So I'll just start off by giving you a brief introduction to the monsoon, and I'm sure you all realize its importance. But the monsoon rainfall in India is important for numerous sectors in the country, because it supplies 80% of the annual rainfall. So the numbers are typically around about 850 millimeters when averaged over all of India during the summer months of June, July, August and September. And this compares to a figure of around about 600 millimeters annually for the whole year in London. So London kind of is a bit grey and wet all year round, whereas India is very seasonal, and you'll see more on that in the next few slides. You'll be well aware that the agricultural yields in India are very strongly tied to the timing, intensity and duration of the monsoon rains, but the wider economy also depends on the monsoon as well. And for example, the big drought that occurred during July of 2002, in which the Indian monsoon was for the season as a whole was about 20% below normal, led to a 3% drop in gross domestic product for India. So we'll think a little bit about where does the monsoon come from, and fundamentally it arises due to contrasts in temperature and moisture in the lower atmosphere and at the surface. And if we think about this in a very simple way, the monsoon comes about due to a land-sea temperature contrast. So what I'm showing here are surface temperatures in degrees Celsius in the spring seasons in each hemisphere. So you've got the bit here, November, December, just before the southern hemisphere summer, and likewise May and June, just before the northern hemisphere summer. And what you can see are that there are some very, very large gradients in surface temperature have built up in several regions of the tropics, not least West Africa and also the Indian region. So very large gradients between, let's say, the Sahara and the Gulf of Guinea out over the Atlantic Ocean, and between northern India, Pakistan and the Indian Ocean, which is itself also very warm. And what this warm air over the land masses is going to do is it's going to rise, and that's going to need to be replaced by air at the surface in order to conserve mass. And as you'll see in a moment, that's going to lead to a monsoon circulation that brings the moisture for the monsoon rains. So the main monsoon regions in the world, we might think of these as the Asian monsoon, of which the Indian monsoon is a part, the West African monsoon, and also then the Australian monsoon. And of course, this happens in the austral summer rather than the northern hemisphere summer. So we have these large temperature gradients at the surface, but we also have large temperature gradients existing through a considerable depth of the atmosphere. So we're showing again some seasonal pictures here. So December, January, February, and June, July, August, so the northern hemisphere summer. And we're showing the temperature averaged over 200 to 600 hectopascals in the troposphere, which is from around about 5 kilometers upwards in the atmosphere. And the reason this is particularly interesting for the India region is because we have this very, very high surface, the Tibetan Plateau, which is up to about 4 kilometers high or so. And this is heated very strongly in spring. And therefore, compared to a similar altitude over the Indian Ocean, it's much, much warmer here than it is further south. So this is really a significant and robust temperature gradient that drives this monsoon circulation over India. So what does this mean in terms of the circulation, the airflow? So here we have pictures of the winter and summer seasons, and we're looking at winds in the lower troposphere, so the relatively near surface winds. And you can see how they have these profound reversals in direction between winter and summertime. And if I just draw your attention to the Asian monsoon region at first, you can see that we have this situation where we have northeasterly winds coming from the northeast over the land. So these are not going to carry any moisture towards India. But in the summer months, the winds have reversed. They're now passing over the warm ocean. They're going to be evaporating lots of moisture and carrying that moisture to India, where it can rain out as the monsoon rains. We get quite a similar behavior over West Africa. Clearly during the winter time, these winds are going to be dry, carrying dry air from across the Sahara Desert. But in summer, we've got a reversal of that wind direction. And now these winds are going to be carrying moisture from over the Atlantic Ocean, the equatorial Atlantic, into West Africa, and that's for their monsoon. And finally, for the Australian monsoon, and remember this is happening in the southern hemisphere summer, these winds are acting to bring warm and moist air from over the Indian Ocean to over northern Australia. But the way that society experiences the monsoon is in terms of rainfall. And this really demonstrates that the monsoon has a profound impact on the seasonality that's experienced by affected countries. So we can see that for Asia and for India in particular, there's very, very little rain in the wintertime, perhaps apart from a few parts of Tamil Nadu. Whereas in the summer, this is really where you see all of the rainfall. And you can see here that there's also quite a distinct distribution of that rain. It's very heavy along the Western Ghats and also along the central India and the Indo-Gangetic Basin and so on, and up against the Himalayas and out into the Bay of Bengal. Southeast India is much drier. That falls under what we call a rain shadow region. So that actually gets relatively little rain during the summer monsoon season. Likewise, West Africa, virtually no rain in the winter, a lot of rain in the summer months during the monsoon. And Australia, in their winter, they get very little rain in the north, whereas in their summer months, they do start to get a lot of rainfall. So the shift in the monsoon between the winter and the summer seasons is very profound for India. Now, the monsoon doesn't just hit immediately on the 1st of June, and it's not uniform across the country as a whole. And what we're showing here is a chart from the India Meteorological Department that shows the traditional onset date at different locations across India. And almost like clockwork, the monsoon starts in Kerala on 1st of June, and it passes in this northwestward direction across the country, taking about 6 weeks to reach the Pakistan border. And I'm not going to go into it during this talk, but during the Encompass project, we have come up with a theory as to why the monsoon propagates in this northwestward direction, which is a little bit unusual given that the winds themselves are coming from the southwest. So that's the monsoon in observations, but how do the models that we use for forecasting the weather and trying to make projections of the future climate, how do they cope with the monsoon? And I'm just going to go over that very briefly in this slide. Just look first at the top line of diagrams here. What we're showing here is what's called a multi-model mean. So this is from about 30 models, climate models, from the coupled model intercomparison project, number 5. And these were the state-of-the-art models around about 5 years ago for the previous IPCC report. And what we're showing here is just the June to September average precipitation over the Indian region. And you can see that it looks somewhat like the monsoon that we know. And on the right, we're comparing that rainfall with an observed estimate from a merger of rain gauges and satellite data that's called GPCP. And what we're showing here is the bias, essentially, in those models. So on average, those models are much too dry over India by perhaps 4 millimeters per day, and they're much too wet over the Western Equatorial Indian Ocean. So in some models, it's as bad as the monsoon being about 50% too dry, or even worse. What's really depressing about this is that the error pattern and the size of the error are quite consistent over several generations of models. And if we go back about 10 years earlier to the models known as the CMIP3 climate models, you can see that the errors are almost as bad as they were until recently. So that was about climate models, but we can use weather prediction models to try and understand how the errors develop. And some centres around the world, including the UK Met Office, they use what's called a seamless prediction system. So the models that they use for climate projection many decades into the future, and for seasonal forecasting for, let's say, 6 months ahead, and also for weather forecasting over the next maybe 5 days, they're fundamentally the same models. They're based on the same physical equations, but they're run at different resolutions, and they have a few other different settings, but it's the same dynamical core to those models. So what we've got here at the top, we've got a picture of a version of the Met Office climate model and its pattern of the summer rainfall. And then we have a comparison of that model with observations. So as you can see, it's too dry over India and too wet over the Indian Ocean. So that's very similar to all of those other models that we've just seen. So the model is quite a well representative of other climate models from around the world. But if we look at a collection of summer one-day weather forecasts for India from the Met Office's numerical weather prediction model, we can see that it represents the monsoon rainfall reasonably well. But if we look at how the biases in that rainfall develop over a 5-day lead time, 5-day forecast, we can see that they're already starting to dry out over India and they're too wet over the Western Equatorial Indian Ocean. So that's very similar to the climate model that's run on timescales of many decades into the future. So this tells us that many of the errors that are likely to be coming about in our climate projections or weather forecasts of the monsoons are things that come about on very short timescales. And in fact, we can blame these on the physical parameterizations that we make in model. So models, they're based on a grid system. They might have a resolution of a few kilometers, a few tens of kilometers, or even 50 or 100 kilometers if they're a climate model. And so we have to make parameterizations or statistical representations of things that are happening at the subgrid scale, such as convection and rainfall. We have to make estimates of those based on the large scale information that we know. And those are called parameterizations. And we suspect that all of the errors that arise in the monsoon come about because of errors in these parameterizations and not due to the long-term buildup of nonlinearities and so on. So this is something that we hope to improve by making better observations of the monsoon. So that led to us having a field campaign which was called Encompass. So the interaction of convective organization with monsoon precipitation, atmosphere, surface, and sea. And we did this in 2016. It was led by myself and Ganapati Bhatt at the Indian Institute of Science in Bangalore. And this was one of 3 projects funded under the NERC and MOES Monsoons Programme, a joint collaboration between India and the UK. Now, as we'll see for the rest of this talk, the Encompass project was very much focused on the interactions between the land surface and the atmosphere above it. But there were 2 other projects in operation at the time. One was BOBBLE, the Bay of Bengal boundary layer experiment. So this was a ship-based field campaign out in the Bay of Bengal. And then a second one, SWAMI, the Southwest Asian Aerosol Monsoon Interactions field campaign. So that was particularly interested in the buildup of pollution aerosols over India, how they affect cloud, how they affect radiation through the atmosphere. And they made use also of the same research aircraft that I'm going to talk about in a moment. So just very quickly, because the number of people involved in this does
You muted yourself. Please unmute.
Andy, you got muted. Andy, you got muted. Yeah.
Can you hear me now?
Yeah.
Yeah, it said that the host muted me, so I'm not sure what happened there.
Yeah. Okay.
So just on the consortium, they deserve attention given the very large effort that was put into running this field campaign. So it involved many institutes. It was led, as I've said, by the University of Reading and the Indian Institute of Science. We had forecasting capabilities provided to us by India's National Centre for Medium Range Weather Forecasting, NCMRWF, which is based in Noida in the Greater Delhi area, but also the UK Met Office. We made use of this aircraft here, the FAM aircraft, and I'll come back to that in a moment. This is a UK research facility. There were also a couple of IITs involved, so IIT Kanpur and also IIT Bhubaneswar. The UK Centre for Ecology and Hydrology, and we'll show some of their work later in this talk, University of Leeds, and also the National Aerospace Laboratories, which is also based in Bangalore, as well as, of course, the Indian Meteorological Department. And I'm not going to go through all these names, but this is just to illustrate what a very large activity this was. And each member of this author list here does deserve their thanks for this very large effort. And most of the slides that I'll show in the rest of this talk come from this paper, which was published in a physical volume in August this year. Okay, so I'll tell you a bit about now the atmospheric research aircraft that we used to carry out this mission, as well as the flight strategy that we used for observing the monsoon. So this is the FAM, atmospheric research aircraft. It stands for the Facility for Airborne Atmospheric Measurement. And you can see a picture of it here. It's a 4-jet engine plane. It's a BAE 146 modified for science use. These were originally passenger aircraft, and they could hold about 80 passengers. But once they've been modified for science, it can seat around about 18 scientists plus the flight crew. Within India, the range of this aircraft can be about 4.5 hours flying time. And unlike most flights in which you tend to fly from one airport to another, the type of flight that we do with this aircraft is to take off from an airport, we fly around for a while, and then we go back and land at the same airport. And that actually causes some challenges to the airports involved, because they don't really understand the concept of doing that. So what can this aircraft do? It has many different instruments on it. It measures the in situ temperature and humidity as it's flying along. It has remote sensing capabilities. It obviously has radar, both for the pilots, but also weather radar. It has LiDAR pointing downwards, so you can sense, you can fly over and you can sense downwards, looking at layers of cloud and looking at perhaps aerosol particles in the atmosphere. You can measure things like turbulent fluxes coming up from the surface. You can, of course, look at cloud. And there are also many instruments on board for looking at atmospheric chemistry. So this aircraft can take live air samples, and it can do aerosol mass spectrometry on those air sort of samples and come up with results as you're flying along. So you can look at what pollution is in the atmosphere and try and determine its origin and so on. So this is what it looks like on board. This is me in the sort of third seat in the cockpit, one of the pilots here. So it is very much like an everyday aircraft. And the purpose of the person in this seat, which was me in this case, is to communicate between the pilots and the scientists in the back in order to try and control the mission and decide what we're going to sample on the aircraft. And this was a demonstration flight that we did for the Honourable Minister in July of 2016. So what things might we be interested in when we're going to fly over India to look at the monsoon? So here's just a map of India, and there's a lot of different things shown on here. The contour lines are showing the mean sea level pressure, so you get an idea of the structure of that. And there's only really one feature to show here, which is the fact that there's what we call the monsoon trough, which is this extended area of low pressure that extends across the Indo-Gangetic plains in northern India. And some of you might know that this area is susceptible to receiving monsoon depressions or cyclonic storms during the monsoon months, which bring a lot of rainfall. Of course, we're up against the Himalayas, which are here somewhere. Everything that is grey on this chart is indicating mountains that are higher than 600 meters above sea level. And of course, then you also see the Western Ghats. So in our flights, there are going to be a number of things of interest, such as flying across the coastline of the Arabian Sea, flying across the coastline of the Bay of Bengal, flying across the Western Ghats. And so we're interested to think about how all of those things might perturb the airflows that make up the monsoon. The other major thing shown on here, and which is particularly interesting in India, are the very large amount of irrigation that is used. And India is one of the most irrigated regions in the world. And this data set here comes from the UN's Food and Agriculture Organization, and it's showing the percentage covered of the land surface in terms of what they call areas equipped for irrigation. So it doesn't mean that irrigation is being used all of the time, but it just means that they have that capability. And you can see that in the northern plains of India, you get to some very high percentages of regions equipped for irrigation. So the idea that we're interested in is, does all of that moisture that might be on the surface in the form of irrigation, does it affect somehow the overlying atmosphere and therefore the monsoon?
Can I ask a question here?
Yes.
So if one looks at these contours, they seem to be moving east-west across the Arabian Sea, east-west across the Bay of Bengal, largely like that. But
Yes.
there is this sudden, steep jag upwards that is when you cross the Western Ghats. Is that something that one can understand very easily? The fact that
I see what you mean. Yes, that may well be an artifact of the way that this is derived. So because this particular field is the mean sea level pressure, obviously when you have a sea level, if you have a land or sea that's at zero altitude, you can actually take measurements of that. When you come to orography, and this is really the reason that we blank it out in this grey color here. When we come to these mountain ranges, it becomes a bit difficult then to interpolate back down to what that could have been. So there may be mathematical artifacts in some of those curves there that cause that issue.
Yeah, thank you.
Okay, so the Encompass project as a whole, what is its scientific interest? So what we wanted to do was to gain a better understanding of the interactions between the land surface, the boundary layer, which is the lowest layer of the atmosphere, maybe about 1.5, 2 kilometers in height, but that varies during the day, and with convection. So convection is really the main process of vertical motion in the air that drives the deep, heavy rainfall of the monsoon. And we want to understand how all of those things are connected to the large-scale environment, and to the variations in the monsoon rains on a range of different time and space scales. How did we go about doing this? Well, it was to combine these aircraft measurements with field observations within atmospheric models at a range of resolutions. So I'm not going to go into the detail here, but we also talked about, and we've also made use of models with resolutions ranging between the typical sort of 20 or 30 kilometers right down to maybe 1.5 kilometers, and even tests at much finer scale resolution than that over India. And the ultimate long-term goal, which I stress is something that this single project can't achieve, is to improve the skill of monsoon rainfall prediction in weather and climate models. So the flight strategy was based on really two aspects. And we wanted to sample the spatio-temporal variations in the monsoon, and focused in particular across two different gradients. So the picture that I've shown here is the evolution of the typical rainfall in the middle of May, the middle of June, and the middle of July, averaged over many years, just to see an example of how the monsoon progresses. And what you can see is that in northern India, you have a gradient in rainfall between the dry deserts of the northwest down to the east coast, drier to wet, and that evolves in time through the monsoon. So we wanted to be able to sample that gradient several times during the monsoon. There's also a gradient that becomes built up very quickly as the monsoon develops, which is this east to west gradient as you go across the Western Ghats mountains. So there's heavy rainfall here, but then much lighter rainfall in southeast India. The dots here, incidentally, are just showing the typical progression rate of the monsoon on those dates from the India Meteorological Department data. So this led to us being based at two different airports, one of which was Lucknow in the north in order to sample the gradient in the north, and the other was Bangalore Airport in the south. This was the old international airport, in order to sample east-west gradients across the Western Ghats into the Arabian Sea and also into the Bay of Bengal. So most of the things we wanted to do were to do repeated samples of the same gradients, but at different times. So in the pre-monsoon and during the monsoon, to see what differences we might see. But we also wanted to undertake what we called flights of opportunity. So, for example, there was a passing monsoon depression that came over central India in July of 2016, and we took the first flight through a monsoon depression, the first research flight since the late 1970s, and as far as we know, the first one to take place over land. So just to look at that again, so there's a map of the flight distribution that took place during June and July of 2016, but also think about how we did it in the vertical. So you've got a chart here showing the longitudinal position of these flights that are largely of an east-west nature. And we've got a scale in terms of atmospheric pressure there, or on the right in terms of altitude. And what you can see is that we tended to take off from the airport base. We fly up to a typical flight level, maybe something like 24,000 feet. We would do a long section, in this case out to the west, somewhere over Jaipur or Jodhpur, and then we would descend to near the surface. And as far as possible, we would try and then do a low level journey, maybe at only 200 meters above the surface, which is really incredible, I can tell you, to fly over India like that for a couple of hours until we're almost back to base and we come to land. The other two flights, which I'll talk a little bit about in one of the case studies later in the talk, we obviously had to get between the two airports. So we were initially based in Lucknow. At one point, we flew down to Bangalore. We took some flights in Bangalore, and then later we returned to Lucknow to do some more flying there. And I'll talk about the two transition flights a bit later in this talk. So how did the monsoon progress during 2016? Well, actually, the monsoon was quite late. This is quite a busy chart prepared by the India Met Department. The red lines are showing on it the traditional onset dates. The green lines are showing what actually happened during that year according to the IMD judgment. And what we found was that the monsoon was a bit later than normal in Lucknow, around about 19th to 20th of June. And what that meant was that we were able to capture some flights taking observations both before that, so in other words, before the monsoon had arrived in northern India, as well as after that. So we could compare the two things together. There were also some ground components of the field campaign. So we're trying to link up the measurements that we're taking in the atmosphere with those that we're doing on the surface. And to do this, we used a series of instruments called flux towers. And we used these to measure the fluxes of heat and moisture, sensible and latent heating, that come up between the surface of the Earth and the lower levels of the atmosphere. And the map here is from a data set called the FluxNet network. And it just demonstrates some of the quality controlled contributions to that data set from around the world. And you can see that it's dominated by Europe and North America, with a few in East Asia. And now it's important and interesting, of course, scientifically, to get some measurements from India for this. But the other problem is that all of those parameterizations that I talked about for representing things at the subgrid scale in climate models, they can only be put together based on observations. So straight away, that tells you something, that if we're designing these parameterizations based on observations that we're getting in very climatically different parts of the world, where they also have completely different soil types, that sort of thing, this is maybe going to be one explanation as to why you get errors in your models. So we installed a series of these new towers across India. You can see these by the green triangles here. So under a different set of surfaces, and those I'll show some information from those over the next couple of slides. So this is just some example flux tower measurements comparing sites at Jaisalmer, which is in the northwest, gets infrequent rains, it's got sandy soils, and we're comparing those with Samastipur, which is in Bihar. So this tends to have a lot of standing water and rice fields, so very, very different surface conditions. And what I'm showing here are what we call the diurnal cycle, so the cycle through the day of the sensible heating, which is the turbulent transfer of heat fluxes from the surface to the atmosphere, and on the right, the latent heating, which is the turbulent transfer of moisture fluxes. And the two sites are in the two colors. And what you can see is that at the Jaisalmer site, which is, remember, a rather dry place, that's dominated by the sensible heating, whereas at the Samastipur site, that's really dominated by the latent heating. So there's nothing surprising there, but it's just very useful to have in situ measurements showing these very large heat fluxes. And you can see that these are up to about 200 or 300 or more watts per meter squared during the peak of the daytime. So I also have some further information on flux tower measurements and how they evolve during the monsoon season. So this is just the movement of a single site at Dharwad, which is in Karnataka, and how it evolves from April, May, June, July, right through to November. And the sensible heat fluxes here are shown in red, while the latent heat fluxes are shown in blue. And what you can see here is that in the pre-monsoon period, there's no moisture around, so those fluxes into the atmosphere are dominated by the sensible heat fluxes. But as we move through into June, they're around about equal. So the monsoon rains are just sort of starting now. As we get into July and beyond, the surface is wet, the monsoon's happening every day or so, and now the main fluxes that you're getting from the surface into the atmosphere are from the latent heat fluxes. And we hope that with some of these towers, measurements will continue for many years to come, and we'll be able to feed this information into our models to improve predictions. And here is Professor Batt installing one of these flux towers in Bhubaneswar. So we had also a ground-based super site at IIT Kanpur. Some of you may be familiar with Kanpur, but they have an old airstrip which is here, and this is actually the roof of the control tower for the airstrip, where we mounted many instruments, including this white object here is what's called a LiDAR ceilometer, and that essentially fires a laser up into the atmosphere, and it's looking to detect the height of the cloud base. And there were several other instruments installed at Kanpur, including a microwave radiometer that can measure humidity and temperature in the atmosphere above it. And we also set up there a radiosonde receiving station. And a radiosonde is what you would otherwise know as a weather balloon. So I'm just going to finish off the talk now with two different case studies of observations from flights that we took place during the field campaign. And the first one is going to be a comparison of the north to south and south to north flights between Lucknow and Bangalore. And we're going to use these to study the evolution of the monsoon between the two dates. And the first of the flights took place on the 13th of June, and the second flight took place going back on the 28th of June. So a gap of just over 2 weeks, in which we'll see in a moment that the monsoon has advanced across the country. So here we are. What we've got here are maps of the accumulated rainfall in 2016 between the 1st of June and the date shown. So the date of the first flight, 13th of June, and the second, 28th of June. And these are rainfall measurements from a data set, a Japanese data set called Aphrodite, which takes in satellite and rain gauge measurements. And you can see here that on the 13th of June, the rainfall had made it only as far as sort of central India and Hyderabad. But by the time you got to 28th of June, it was well up into northern India, and certainly covering Lucknow here. And again, the dotted lines are just showing the traditional IMD onset dates around about that time. So we'd expect the monsoon to have covered most of the country by 28th of June. And this chart, in fact, shows that the monsoon was a bit delayed in 2016 compared to a normal year. And we're interested in contrasting other observations between the two dates. So here, for example, you can see a picture of what's called a change in the volumetric soil moisture between the 13th and 28th of June. And this is a percentage change. And this is based on a satellite microwave measurement of soil moisture. And what you can see is that for most areas of central and northern India, the soil has become much moister between the two dates. And that is naturally following from the fact that we've now got rainfall coverage over most of the country. So what else did we see different between the two dates? So this plot is a little bit involved. What we've got is a height latitude section going from the south 10 degrees north to 30 degrees north, going through central India. And the background shading is showing a quantity called equivalent potential temperature, or theta E. And this quantity takes into account both the temperature of the atmosphere as well as its moisture content. And if you raise either of those quantities, this theta E value goes up, but in a non-linear manner. So it has units of Kelvin. And it's from a data set called ERA Interim, which is what's called a reanalysis data set, which is a methodology of basically taking all of the weather observations that exist everywhere in the world and putting them into a forecasting model, but updating that every day with the latest observations. And so that allows us to kind of see what any point in the atmosphere might be doing in terms of wind and temperature and so on, even if we don't have any direct observations at that point. But the useful thing is we can compare that reanalysis data set with the actual in situ observations that we took from our research flights. And those are shown by the circles measured here from our takeoff, in this case in Lucknow, ascending to upper levels, flying at high levels. We did a bit of a sort of a profile descent in the Hyderabad region and an ascent again, then a high level flight, and then a descent down to Bangalore. So the fact that mostly the colors align well with the reanalysis suggests that there's a good agreement there. And actually the reanalysis is doing quite a good job of representing these observed quantities. But the main feature I want to point out in the two diagrams and how it's changed between 13th and 28th of June is the disappearance of this large blue feature at the middle levels of the atmosphere, around about 600 hectopascal of height, which is about 4.5 kilometers. And what you can see, what we interpret this as is what's called a dry intrusion. So the fact that the air at that level is dry, it lowers this quantity. And this is a feature in meteorology that's going to act to prevent deep convection. It's going to act to prevent rainfall. So as we get to the 28th of June, this feature has retreated far southward across the country. It's sort of been eaten away from the surface, and this is going to allow deep convection or the monsoon rains to occur. So that was quite nice to see. And the next slide just goes into that in more detail, but using a different type of observations. So each of these 6 panels, A to F here, is taken from one of these launch sites shown in this diagram, going from south to north. And these are radiosonde profiles. So these are measurements taken from weather balloons, which are launched twice a day from several locations all over India. And we've chosen the ones aligned to this flight route to see what would happen. Now, this is a very complex diagram. I'm not going to go into all of the details of it. It's known as a tephigram. Essentially, on the left, you have pressure height in the atmosphere indicated by the surface being at 1,000 hectopascals, all the way up to the upper troposphere at 200 or 100 hectopascals. And broadly speaking, the x-axis on this diagram is temperature, with higher temperatures to the right. And the red curve is the everyday absolute temperature that we measure with a thermometer. The blue curve is something called the dew point temperature, which also takes into account the humidity of an air parcel. And if the blue curve and the red curve overlap, then that means that the air parcel is saturated. It's as humid as it can possibly be. And this helps weather forecasters understand whether there may or may not be convection and rainfall. So what we see in going from south to north of India in the pre-monsoon time of 13th of June is that the south of India is moist. It's got what we call a moist profile. The blue and red lines are quite close together. But gradually, as we go northwards across the country, all the way up to Lucknow, the air is getting much drier. So this blue dew point temperature curve is moving to the left. So we wanted to see how this changes as we move through time to the 28th of June, when, remember, the monsoon has progressed over much of the country. So what I'm going to show you is that the whole atmospheric column will have become much moister, even progressing far north towards Lucknow. So there's the same information for the 28th of June, and then you can see that for all cases, the blue curve, which is the dew point temperature, is much more moist. It's showing much more evidence of saturation as we go northwards through the through the country. So this really confirmed some of the hypotheses we had about the role of that dry intrusion in controlling the rate of the monsoon onset. And I don't have time to go into detail, any more detail about that study, but it's very interesting. And if you wish, you can read about that in a paper by Doug Parker and co-authors in the Quarterly Journal of the Royal Meteorological Society. So what some of the early outcomes of Encompass have shown is that there's an important interaction between a mid-level dry air intrusion and the advance of moist tropical air in controlling the advance of the Indian monsoon. And if you're interested in the details of that, then please do ask later about those studies. So finally, I just want to go through another case study. And this is again relating to soil moisture, but this is specifically going to be about how very small gradients in soil moisture over the surface of India might lead to the initiation of storms, and therefore might help us to predict when the rains will occur during the monsoon. And these gradients in soil moisture might come about from two different things. One of them could be preceding rainfall during the monsoon. The other could be that irrigation that I mentioned earlier, which is going to be particularly relevant in northern India. And in fact, it was very interesting when we were flying over northern India, just looking down and seeing all of the different irrigation practices in the Ganges Basin area, all the sort of canals and tanks and various features that are adding moisture to the surface. And a lot of that is pumped out of the groundwater. So it's sort of additional water that's not part of the everyday water cycle of the monsoon. So this case study is based on a single research flight that took place between Lucknow, which was our airport base, and then over towards Jaipur and to the Jodhpur area, and then back. And what we did the initial flight at high levels to take some information about the cloud structure and what the whole atmosphere was looking like. And then we returned on our flight at low levels. So that's shown by the black line here. That's the route we took. And the average height along that black line was at an altitude of only 191 meters above the surface, which is just incredible. But that allows us to both sample the air that's very close to the surface, as well as looking at features on the surface and how they might be affecting that air. So there's various features from this low-level track that are shown in this diagram. The scale on the x-axis is in terms of the distance along that low-level track. And then there's various quantities observed from the aircraft to show you here. The first is a measure of potential temperature. So this is a variation on temperature that also accounts for the changing effects of density as you go up higher in the atmosphere on that temperature. And as you can see, as we flew along that region, there was a sharp gradient in the temperature of about 5 Kelvin at a particular region along the track. At the same time, there was also quite a change in the specific humidity measured in kilograms per kilogram of that region. So that's how much moisture is in the atmosphere. And there were also strong features in the winds relative to the aircraft. So particularly this feature here, which is V along, this is the along track winds measured from the aircraft. You can see there's a change in winds going from one direction to the other direction. So actually what we're demonstrating here is something called convergence. So at this point, and I'll show you this on a map in a moment, there's going to be converging winds at low levels in the atmosphere. And just another thing to highlight, this is the downward solar radiation as measured by the aircraft. And you can see a big change between what looks like clear sky conditions for the earlier part of the track into what looks like patchy cloud for much of this part of the track. So looking at it in terms of a map, there's quite a lot of information on this diagram, but what we've got in the background, firstly, it's a latitude longitude map over the region of the flight track. The background colors come from the interim reanalysis that I've mentioned before, and this is measuring the potential temperature. And you can see that there are strong gradients in that potential temperature in this low level of the atmosphere as we fly over it. The colored circles are the same quantity, but as measured by the aircraft. So you can see that there are some disagreements with the large scale data set, but the general pattern is the same. The black vectors are showing you the wind direction in meters per second, coming from the reanalysis data, and the white vectors are showing you the values for those winds, but actually measured by the aircraft. And what you can see, and this is consistent with the previous diagrams that I just showed you, was that as we go through this strong gradient in potential temperature near the surface, there's also a convergence of the winds between these 2 points. And that's going to be important to us because in order to conserve mass, where we have low level convergence in the atmosphere, that has to give rise to ascending motion, which has the potential to become storms and to lead to convection and rainfall. So I just want to show and think about, well, why might those gradients in the potential temperature of the low level of the atmosphere exist? And what it's due to is, in fact, soil moisture. So the picture on the left here is showing a proxy measurement for soil moisture that's derived from a satellite, an instrument known as GPM, and it's from the ratio, what's called a polarization ratio that's derived from brightness temperatures at 10.7 gigahertz. And what you can see here is there are very large gradients in the soil moisture at various sites along the flight route, and of course at other places as well that we haven't measured with the aircraft. And these could be due to previous rainfall, or they could be due to irrigation. So the blue colors here are illustrating wetter soils, and the reds are illustrating drier soils. And so the hypothesis, and it's been shown in many other areas of meteorological research as well, is that these gradients in the soil moisture along the surface, they are associated with different amounts of drag, frictional drag, for air flowing over them. And so if you get a change in that, you can get a convergence generated, which leads to convection. So the flight itself took place earlier in the morning, when it's quite unusual for deep convection and heavy rainfall to occur during the monsoon. So what we looked at later were satellite observations to determine whether deep convection was occurring. And we have a measure here called the cloud top brightness temperature, which is related to how deep a cloud is. Essentially, if our cloud is deeper and deeper and deeper, such that the top of the cloud is getting higher up in the atmosphere, its top surface is going to have a much cooler temperature than if it's a shallow cloud that's relatively near the surface of the Earth. And we can infer that from infrared satellites, such as this Meteosat satellite. And the deep blue colors here are showing areas where there is very, very deep cloud, and therefore likely to be rainfall in the tropics. And so this is our flight track. You can see, obviously, these white areas are showing visible areas of shallow cloud, but the deep blue colors are showing areas of deep raining cloud later in the monsoon. So this is just a single case study that's demonstrated that the gradients in soil moisture at the surface can perturb the overlying atmosphere, and later in the day, when the surface has heated up a lot more, they can lead to deep convection and rainfall. So the outcomes from that case study, we've shown that mesoscale, or in other words, gradients on scales of a few kilometers, gradients in soil moisture structures can be important in the initiation of deep convection over India. Similar work that's previously been done in field campaigns over West Africa have indicated that such surface features have been linked to a very high proportion of storms that occur during the monsoon. And the message here is that, well, if a lot of these storms are being generated by gradients that are occurring on scales that are smaller than the grid scale of your typical model, then how are you going to represent them in those models? You might be missing something about when storms are being initiated in weather and climate models. So what we need to do to follow this up, we need more of a general assessment of the importance of soil moisture gradients through the whole monsoon. So over different parts of India and how they vary in time as well. And that's something that can be done with exercises looking at large scale satellite studies and so on, in conjunction with reanalysis data in order to look at the winds and so on. Okay, so I think that sort of brings us to the end. I'll just give you an overall outlook from the Encompass project. So Encompass was a field campaign based around 22 research flights, flux towers that we installed at the surface, as well as other instrumentation. Most of the data from the field campaign is freely available. You do have to register, but you can get hold of it on the UK's Centre for Environmental Data Archival. If you search for the South Asian monsoon here, you can actually get hold of that flight data. So Encompass has already demonstrated the importance of soil moisture patterns and land-atmosphere interaction more generally for the monsoon. And there are other Encompass findings that I've not gone into here for the interest of time, but we've led to important connections being made between the large-scale circulation patterns and being able to forecast rainfall in the Western Ghats region. So in particular, whether that happens offshore or onshore. And we think that could be quite useful. Really, I think field campaigns such as this, they tend to give you some answers, but they don't give you all the answers. And in fact, they motivate us to think about more observations and being able to have further field campaigns and so on. But there's really still a great deal of work to be done in sampling the monsoon and testing models with those new observations in order to try and improve forecasts. So with that, all that remains really is to acknowledge the other main sort of teams that were involved in the field campaign. One thing that particularly was gratifying about the field campaign was the number of young scientists that were sort of enthused by observations of the Indian monsoon. And this is a group of them from Bangalore on a visit to the aircraft to go and have a look at it when it was based out there. And of course, the Met Office and various computational support and so on. So I'll just thank you once again for undertaking listening to my talk. And we do have a special journal collection that's come out very recently in the Quarterly Journal of the Royal Meteorological Society, which does have some of our results in, if you're interested to see more. And I can take any questions now.
Thank you, Andy, for a very comprehensive view, different view of Indian monsoon, and also bringing us the results of Encompass. It was really a very illuminating talk. The talk is, of course, open for discussion and questions now, questions, comments. So we'll first take questions from Zoom audience. I see a hand, Dr. Vivek Datar. Yeah, please unmute and ask your question.
Yeah, can you hear me?
Yeah.
I can, yes.
Yeah. Okay. So my question relates to the role of forests in this whole monsoon cycle. Is there any explicit role of the greenery associated with forests, or is it primarily dominated by agricultural greenery?
There is definitely evidence in the literature that forest cover and agricultural surfaces, they make the monsoon behave in a different way. And one of the things I'm sure you're familiar with is the concept of the Green Revolution and the way that agricultural lands were expanded massively from the 1970s onwards, maybe even earlier. And I know of a few studies in which they've compared the impact of changing the land cover between forest, let's say in the 80s, and more agricultural land today. And it does definitely have an impact on the monsoon. One of the things it changes is the what's called the surface roughness, which is a way of determining, it's sort of a coefficient of determining how momentum is transferred between the atmosphere and the surface. It's like a frictional coefficient. So that's different. The albedo is different. So the green surface is darker and it reflects solar radiation in a different way to the tends to be sort of brighter or more yellow sort of surfaces of agriculture. And of course, the way that the forest canopy intercepts rainfall is very different to a way that an agricultural field does. So there is evidence in the literature to suggest that the change to agriculture has altered the monsoon slightly, potentially making it a little bit drier or feeding back on that and drying it.
Okay, thank you.
Thank you, Andy. We have another question from Hariom Sogarwal. Hariom, you can ask your question.
Yeah. Can you hear me?
Yeah.
I can, yes.
Okay, so my question is, what is the uncertainty in position measurement of this like monsoon and this weather conditions? Can you comment on it?
That's actually a good question. And there is somewhat of a dark art to defining. If I go to slide 7, bring that one up. There is somewhat of a dark art to defining exactly where the monsoon is, and you know the IMD struggle with this, as do everyone else, because what you can actually have is that before the monsoon starts itself, you might have some pre-monsoon showers, and so they can lull you into a sense that the monsoon started, but maybe a couple of days later they go away, and actually that you get into a situation there of having a false onset. And so what we tend to do is to make sure that rainfall has persisted for a good period, such as 5 days at a given location, before defining that the monsoon has arrived, because otherwise we do get into difficulty with declaring whether the monsoon has happened or not. I know that the IMD, you know, for when the monsoon does begin over Kerala, they're also looking at some other features in the atmosphere, such as the outgoing long wave radiation. So that's kind of measuring the cloud top temperatures, and they're looking at that on a large scale, not just at a local point. And they're also looking at the wind speed over a particular region of southern India as well. So there's a number of different factors that go into their decision making about whether they declare the onset or not.
Okay, so it means it depends on like other parameters, other like wind flows and.
Yeah, that's right. Yeah.
Okay, thank you.
Thank you. Maybe we can take something from YouTube, Satya.
There's one question Professor Manchanda has typed in.
Oh, okay. Yeah, I'll just look at the chat 1 minute. Maybe Professor Manchanda, you want to ask the question?
Yeah, can you hear me?
Yeah.
Yeah, my question was, has somebody considered the role of charged aerosols in these models for monsoon rain predictions?
Yes, so aerosols are considered in models, and we tend to think of aerosols as having two major categories of impact on the weather and climate. The first is what we call the direct effect, or what we call aerosol radiation interactions. So if you have, so let's say some sulfate type of aerosols, these tend to be very reflective. And if you imagine we've got a layer of sulfate aerosols in the atmosphere, they're reflecting solar radiation back up to space, and they're perhaps preventing some of that getting to the surface. So that will actually lead to cooling of the surface. And there are a number of different studies, and I will talk about this more in my seminar on Wednesday, showing that actually the prevalence of sulfate aerosol emissions have reduced the monsoon since the 1950s. So the monsoon's not as wet as it used to be. There's another type of aerosol as well called black carbon or soot that often comes from cooking fires in India. And that tends to be an absorbing aerosol rather than a reflecting aerosol. So again, it's preventing radiation reaching the surface, but it's doing something rather different. So instead of allowing that radiation to reach the surface and sending it back to space, it's actually absorbing and then re-emitting at some layer in the atmosphere, wherever that happens to be. And of course, both of those two things I've talked about can have interactions with the clouds. And there is a further aerosol effect, which we know is the indirect effect of aerosol, or the so-called aerosol cloud interactions, and that really has profound impacts on cloud microphysics. So both on the number density of cloud condensation nuclei, which are the sort of particles around which water droplets coalesce in clouds, but also on the albedo of clouds. And the more of this you have, the brighter the cloud gets, and then the more the cloud reflects solar radiation. And really, this second category of effects is really quite uncertain. It's difficult to measure, and we do model it in weather and climate models, but there are very large uncertainties associated with it, and it's something that needs a great deal more research in order to understand.
Thank you. Satya, maybe we can take a question from YouTube first.
Also a question from Arnab. Maybe you can take it and then we can go to YouTube.
Arnab, can you ask the question?
Yes. So many of these models actually look at the total amount of precipitation or whatever it is across the monsoon. But one thing we've probably, I don't know if it's just, anecdotal, but it seems like there are also more extreme variable events. So very spells of very high localized rainfall followed by not so much rainfall for a few weeks, and then again very high localized rainfall, etc.
Yeah. So
are there efforts at modeling this variability within the monsoon season itself?
Yes, very much. And there's sort of two aspects to your question. I'll come to the second bit first, which is, as monsoon modelers, we all recognize that it's really these kind of active and break events that's of most interest to, certainly to agriculture in India, but also to other users of water resources. And there are great efforts that have been ongoing for many years to understand what is it at the slightly larger scale than India that controls these active and break events. And there is a phenomenon in the atmosphere called the boreal summer intraseasonal oscillation, which is operating at a larger spatial scale than India. It's covering also the Indian Ocean, the maritime continent of Southeast Asia, also parts of East Asia and the Western North Pacific Ocean. And understanding how that thing evolves in time can help us explain how and forecast how the monsoon will undergo active and break periods of a few weeks ahead. But the first part of your question alluded to changes in extremes, and it has been recognized for quite a long time now that as the world as a whole is warming, the warmer atmosphere can hold much more moisture. And this is due to a physical relation called the Clausius-Clapeyron relation, which states that there's a very nonlinear relationship between temperature and the amount of moisture that can be held in the atmospheric column. And so if you imagine, I mean, this is just a simple way of thinking about it. If you imagine in the heaviest rainfall event, all of the moisture in the atmosphere above you comes out, then clearly if that atmosphere is hotter, then there's going to be more moisture to come out in those extremes. And this is something that's sometimes referred to as an intensification of the water cycle. And there's really good theoretical, observational and modeling evidence for it that this indeed has been happening over the last several decades, but will continue to do so in the future as the world warms.
Thank you. I think there are some questions on YouTube. We will first take some from there and come back to the Zoom again. Okay, Vivek, we'll come back to you after these two questions. Yeah.
Sure.
Can you take the YouTube question?
One question from Uttam Pal. The question is as follows. Monsoon is seasonal rainfall, which is due to land, water, temperature difference. What is the origin of non-seasonal rainfall, like what happens in Europe?
Okay, so one example, well, there's two things I could say to that. One is that there is a small winter monsoon for parts of India. So particularly if you're in Tamil Nadu, and also if you were in Sri Lanka, you'd be getting more rainfall in the winter months. And that's because the winds are coming down from the northeast, and they are passing over the Bay of Bengal before they hit those regions, and so that's supplying them with moisture. But especially if you're in northern India and parts of Pakistan, you may also get rainfall from systems which are known as westerly disturbances or western disturbances. And these are features that are sort of vortices that come across on the jet stream from the west. And as they approach the mountains of northern India and Pakistan, they can sometimes draw in moisture from over the Arabian Sea, and they can lead to rainfall at that time of year, especially in the winter. If you're interested in that, please do try and attend my talk on Friday, because I will be talking extensively about those features.
Okay, so can I take another one?
Yeah.
This is from Mukesh Singh Raghav. Can equatorial waves in shallow water theory help understand some aspects of Indian monsoon?
Yes, definitely. And perhaps for some of the other people not familiar with the concept, shallow water theory doesn't just apply to water. So the shallow water equations can be derived for any layers of fluid, and in the simplest form we might think about 2 layers of atmosphere, and indeed for the tropics and for the regions close to the equator in general, there are a number of interesting wave features that help us to predict variations, short-term variations in the monsoon. So one of these are a type of wave called Kelvin waves, which is something that moves eastwards, although you tend to need to be quite close to the equator for those. Another is what's called equatorial Rossby waves, and they move westwards. You can be a little further away from the equator, and India can come under the influence of those, and so that could give periods of alternating rainfall. And finally, there is something called the Madden-Julian oscillation, which is an eastward propagating wave that is sort of based around the equator but extends to higher latitudes. And that is based on the wave theory, so it has some similarities with the things you might get from shallow water equations. And it also has some relation to the observed boreal summer intraseasonal oscillation and the active and break periods of rainfall that we get in the monsoon. So to summarize, the study of equatorial waves and waves from the shallow water sort of framework, they give us great insights to the variations of weather in many parts of the tropics.
Thank you. Maybe we'll take now one last question from Zoom. Vivek?
Yeah. This question, I don't know whether it's directly related to the monsoon as a whole, but one tends to think that in the beginning of the monsoon and towards the end of the monsoon, as it's receding, you have big lightning and thunderstorms.
Yeah.
Now, explanation for this?
Yeah, it's not something I've done research into personally, but yes, certainly in northern India, and in fact the Lucknow area, the pre-monsoon storms are associated with a lot of thunderstorm activity and lightning strikes, and certainly I know I have colleagues that are working on that type of thing at the moment, and it's a particular concern, of course, for agriculture because of the number of farmers that are killed working out in the fields every year due to the lightning. So although it's not something I have expertise in myself, there are now representations of lightning strikes in models. Of course, it's very difficult to predict, but in a statistical sense, you can make some inference about lightning occurrence. So people are working on that now, yes.
No, why I asked this question is because there's some work done in the Cosmic Ray Laboratory in Ooty, which said that they have measured voltages on some of these clouds in these thunderstorms, big thunderstorms, which are, a factor of maybe 3, 4, or 5 larger than what one expects. So it's something somewhat unusual.
Yeah, so that's very interesting, and part of that could just be the very deep nature of the clouds in the tropics that can go to very, very many kilometers
Yeah,
high.
that's right.
And the other part, there could be some interesting features to do with the cloud microphysics and the aerosol. But I think these are very open research questions that we need to do a lot more work on.
Okay.
Thank you.
Thank you.
Thank you very much, Andy. I don't see any more hands. So let me once again thank you for a very comprehensive and very informative talk. And I now give back the mic to Satya for final comments.
Thank you.
Yeah, thank you, Dr. Andy Turner, for this very, very interesting talk. And also, this is something which we keep experiencing every day, every season, but never really understood. There are so many kind of technicalities involved in, in the prediction and also measuring. And it's very interesting, the kind of equipment and the tools that you use, the simulation tools and other tools that you use. So it was very, very informative. And we look forward to also your talks later this week. And so with that, let me thank you and also the IPA and IOP for organizing this series. And we look forward to other talks as well. Thank you very much.
Great. Thank you very much for your attention and your questions.
There was a request about the next two talks. So the next two talks are going to be held, one by University of Hyderabad on Wednesday at 5 p.m. And the third talk will be held at on Friday, 30th October at 5 p.m. by IT Roper. The links, the YouTube links for both these lectures are available on the IPA webpage. And the same Zoom link will work if you want to join by Zoom. Thank you.
Thank you.